Welcome to Guided Study Group, week 8 of Math 140. And so this week we're gonna do section 3.2 and 3.3, which is gonna use a lot of the first derivative, and it's gonna have a lot of graphical applications, which is we're gonna see in like a minute in the review. But I guess you guys have already seen it in the lectures, so let's go over them. So first is section 3.2. So in 3.2, there are two main things that you should just really pay attention to. It's the Rolle's theorem and the mean value theorem. So, and one of the things that I would highly recommend to remember for the sake of remembering is that the Rolle's theorem is just a specific case of the mean value theorem. So if you can first remember the mean value theorem and then do some like adjustment in, say like you add in one adjustment, which is this last one, then you get the Rolle's theorem. So both of the theorems says that if you have f be a function that satisfies the hypothesis, so it both have to satisfy f is continuous on a closed interval, and f is differentiable on that open interval. For the Rolle's theorem, you need one additional condition, which is the value at the two ends are equal to one another, fa equal fb. Then there's a number c such that you have f prime of c equal to 0. However, in the mean value theorem, it's more general in the case that it doesn't need that conditions, but it say there will exist a number c in that interval such that f prime of c is equal to fb minus fa over b minus a. As you can see here, if you have fa equal to fb, this one is going to be equal to 0, which is take us back to the Rolle's theorem. So I would highly recommend remember it in this way because it's really easy to remember, especially when you have to deal with a lot of theorem and so on. And I would say another thing is that these things must be remembered, because I remember in my Math 140 final exam, it asked something about, well, not final, it's the midterm too. It asked me something about a Rolle's theorem, and in a good half an hour, I couldn't remember what exactly it is, but because I didn't. Well, I mean, my practice in learning math is that I never actually remember the name of theorem. I know that theorem, but I just never remember the name. And so, but I'm sure like in your midterm too, you definitely see it in the exam. So just know these things. Then we have some smaller thing. It's another theorem saying that if you have f prime of x equal to 0 for all x in an interval, and f is constant on a to b. And this is easy. If you can see, it's like a straight line like this. So if you have f prime of x equal to 0, so the slope of the tangent at all points at 0, and it has to be in this form, which is a straight horizontal line. Then you have f is constant on AB, because it's just a value at, say, a value at big A. Then we have corollary, so like one of the consequences. If you have f prime of x equal g prime of x for all x in A to B, then f minus g is constant on AB. That is fx is equal to gx plus c, where c is a constant. Now this one is gonna come to the definition of antiderivative that we learn later in this course after midterm 2. But there was one way that we can think about this thing. So say if you have two lines, or maybe like even just two parallel curves, you can see the fact that the slope at every single point are equal to one another. Same thing here. Then you can see the fact that this curve over here, say this one's G, this one's L, it's just F that shift up a certain value. So say shift up 3 units. So that's the C that we're talking about here. So I mean, we're gonna get back to this after midterm 2 as well, but in midterm 2 there can always be something that they ask you about this corollary. So Some of the representative problems that we can see in this section is that prove that some equations, so say you're given an expression of fx, a function fx, and you have to prove the fact that this equation has exactly one real root, maybe in a, b. And so you can achieve that by using the mean value theorem. And I don't think I have it in this example, but I'll try to put it into the review sections where we go through all the things again. So I'm just going to put it review of midterm 2. Make a note to myself that I have to mean value theorem. Exactly one root. Okay. Yeah, I'll try to put that in the review for midterm 2. Or you can be asked something like, if you have f equal to that and f prime of x smaller than a number for all x in I, how large can f possibly be? And this one is going to use a mean value theorem when you have f prime of c is equal to fb minus fa over b minus a. But you know f prime of c is smaller than or equal to some number. So eventually, at the end of the day, you're going to solve maybe like fa smaller than or equal to something, or fb bigger than or equal to something. You try to solve for these. So, and where you can find it. See, like for the first two type of problem, it's not really clearly demonstrated in the lecture or maybe in the exercise that you were given, but these are the very helpful applications of the mean value theorem that we never actually expected, but it can be used. Finally, is asking if there exists a function f such that fa equal to something, fb equal to something, and fc smaller than or equal to, bigger than or equal to for all x. And so this again will come back to this. Now let's go with the example. And so just to let you know, like the example that I'm gonna be doing here is gonna be way easier than these, because we're just gonna try to practice in this sections first. But at the end of like the materials of midterm 2, where you try to put everything together, that's when you start to elevate everything onto another level. But here for now, try the basic thing first and see if you actually master the hypothesis of the 2 theorem. So first example is question 6. You have fx equal to x cubed minus 2x squared minus 4x plus 2 on an interval of -2 to 2. It asks us to verify that the function satisfies the free hypothesis of Rolle's theorem. Find all numbers C that satisfy the conclusion of Rolle's theorem. And so the way that we're going to do this now is that, let's say the free hypothesis of the Rolle's theorem is that f has to be continuous on the closed interval -2 to 2, which is the case here because it's a polynomial, so it's continuous everywhere. And it's differentiable on -2 to 2. Again, it is also because it's the polynomial. So the thing with polynomial is that it usually is very easy to talk about continuity and differentiability. So just like the first thing you're going to do with these is when you're given a polynomial is that you know the fact that it's continuous and differentiable everywhere. This is the open interval. Last one is f -2 is equal to f2. F -2, if we plug in, we're going to have -a, -8 plus 8 plus 2. It's going to be -6. F of 2, when we plug in, is 8 minus 8 minus 8 plus 2. So it's again -6. So it's satisfying free hypothesis of Rolle's theorem. And the entire point of this exercise is make sure the fact that every single time you try to use Rolle's theorem or mean value theorem, make sure that it always satisfies the hypothesis first, so that you can actually use it. If not, the theorem is not eligible to be put into the problem. Now find all of the value C. So the next part is find C, such that f prime of C is equal to 0. Because in Rolle's theorem, it's a special case where fa equal fb, and so f prime C is going to equal 0. To do that, you're going to have f prime of x is equal 3x squared minus 4x minus 4. Things should be like quick as right now. The way that you guys do it shouldn't be but like before. It's gonna be, now you should be able to master the way that we take derivative. And so if you solve for set it equal to 0 and solve for x, so if I just, this is just algebra, so I'm just going to use it quickly with calculator. So I have x equal 2 or x equal negative 2 over 3. So this is my answer for this part, this questions. So again, just make sure that you always check on the three hypotheses of Rolle's theorem that a function has to satisfy before you apply it into the problem of that function. So on a similar thing, we're gonna do example 2, and this is kind of the same thing, but let's look at it. You have fx is equal to 2 minus absolute value of 2x minus 1. It's asking, show that there's no value of c such that is satisfying the conclusion of the mean value theorem. Does it not contradict the mean value theorem? Well, let's look at what function this is. So this is it has an absolute value. So the way that we're going to do this is that we're going to separate into the piecewise function. Remember, absolute value of a is equal to a if a is bigger or equal to 0. Negative a if a is smaller than 0. So based on this one, this is how we want to do it. This is going to equal 2 minus itself. If you have 2x minus 1 is bigger than or equal to 0. Or you have 2 plus 2x minus 1 if you have 2x minus 1 is smaller than 0. Or it can actually equal, now we're going to do just algebra, like 3 minus 2x if x is smaller than or equal half. 2x plus 1 if x is smaller than half. So this is the functions that we have. Now, looking at this, so to use the mean value theorem, we should check on the hypothesis first. So the hypothesis is that check if fx is continuous on 0 to 3 and differentiable on 0 to 3. Now continuous, again, back to the continuous is what you have to satisfy the three special conditions. So for continuous, let's check. You have limit of x approaching half minus of fx. It is going to be limit of x approaching half minus of 2x plus 1, because it's going to be on the left. So this one is equal to 2. Limit of x approaching half plus of fx is equal to limit x 3 minus 2x, which is going to equal to 2. So, and then you have f of half is equal to so this thing is half is going to equal 2. So we have the fact that fx is continuous on 0 to 3. Now, next part is to check the differentiability. Should so just give me a second. I need to add a slide in here. So let's get on that. So check the differentiability. So now we're gonna have, so f prime of x also have two functions. So it's gonna equal -2 if you have x is smaller than or equal to half, or it's gonna be 2 if x is bigger than or x is smaller than or equal to half. Now so as you can see in the fact that not equal. So as you can see, limit of x approaching, so when we talk about differentiable, let's see a way that I can put it. So as you can see, the fact that limit of actually f prime of half does not exist, because you can see back into the function here, when x approaching half plus, so it's going to be this upper part. F prime of x is going to approaching -2. When x is approaching half minus, f prime of x is going to approach 2. So the value of f prime of 1/2 does not exist, because actually you can say the fact that f prime of x or f prime of x is not continuous at half, because limit of x approaching half minus of f prime of x is different from limit of x approaching half plus f prime of x. So it's just going to be the case here. So if you put it in the graph, so I would say this is the graph of f prime of x. So this is half. So on the left, it's going to approaching something of -2, and on the right, it's going to approach something at 2. So the value of this thing, this is not continuous, because it's not differentiable everywhere on this interval. You can see a clear discontinuous here. So this is so our conclusion is that f of x does not satisfy the condition of the mean value theorem. Therefore, you can conclude the fact that there might not exist a value c that f prime of c equal to fb minus fa, you can put it f3 minus f0 over 3, or it's -4 over 3. So that is my conclusion. So at the end of this question, it's saying if you have a function that doesn't satisfy the condition for the mean value theorem, so it doesn't. So the function will not satisfy the conclusion of the theorem because it's not eligible to apply the theorem in it. So this is kind of like a challenging one, especially when it comes to evaluate the differentiability of the function. It's been a while since you guys actually touch on it. So if you like confused the struggle here, I would highly recommend go back and have a quick review on differentiability. If there's no questions for this, I'll go to 3.3. So 3.3 is where you actually use the first and second derivative to come to the conclusions about the graph of the function that you're evaluating. So for the first derivative, we have two conclusions that we can draw from. It's that if the function is increasing or decreasing, or if the function or if you have the local maximum or local minimum at a point, or nothing at all. So first is using the first derivative. So this one is going to be the first derivative is increasing or decreasing. So if you take derivative of a function and it's bigger than 0 on an interval, then it is increasing on that interval. And on the other hand, if it's negative, it's going to be decreasing. The first derivative test also allowing you to identify if you have C is the critical number of a continuous function. If you have f prime of x, change the sign from plus to minus. So it go like increasing to decreasing. Then you have a local maximum there. Graphically, it's easy to see. Again, if you go from negative to positive, decreasing to increasing, you have a local minimum there. And if it doesn't change the sign at all, there's no local maximum at C. And trust me, this thing is possible, especially when you have like rational function. It usually is the case that you're gonna have a table like this of f prime based on x. You're gonna have some value like C here that's undefined, and then you have A and B. And you're gonna have a negative here, and a positive. So from here to here, it go from negative to positive, easy to see that this is the minimum. However, when you go from smaller than C to bigger than C, f prime doesn't change the sign, and the overall is just going to be decreasing. So the graph is going to look something like this. So it's going to have some maybe something with C that just keep gonna either decreasing this way, or it can decrease and it doesn't define, it's not defined, so it's not continuous as C, and it continues again. So that might be the case. There are several scenarios. So in this section, just one thing to keep in mind, like don't restrict your imagination anywhere. Just make sure that you check through every single calculations and maybe algebra, and that'll be good. Then it's come to the application of the second derivative is when you use it to evaluate the concavity. So some definitions to note here. If you have the graph of f lies above all of its tangent on an interval I, then it's called concave upward. How is it look on the graph? So if you have like this and your tangent, so this is your graph and this is your tangent at the point. So if the graph lies above all of its tangent, so concave upward is gonna look like that. But when it's lie below, so say here, so this is called concave downward. Also, there's the definition of an inflection point, which is gonna be the focus of the second derivative test. Is that you have a point. If you have a point on a curve, it's called an inflection point if f is continuous there and the curve changes from upward to downward concavity, or downward to upward. So say if you have a graph that looks like this. So see clearly here, on the left is concave downward, on the right is concave upward. So this point is called the inflection point. Just how it graph, or you can change the other way back. So this one is also the inflection point. Finally, you have concavity test. So to determine if a function is concave upward or downward on that interval, you look at f double prime of x. So second derivative. If second derivative is positive for all x in that interval, it's concave upward. And again, if it's negative, concave downward. Pretty easy to understand and remember. Next is the second derivative test. So second derivative test, as I say, is usually, well, sorry, I forgot. Like the second derivative test doesn't actually deal with inflection point. Yeah. So second derivative test, I think there was like one of the definition of the inflection point. Oh yeah, here is just this one. When it go from concave upward to downward, f prime, f double prime of x. So f double prime of x change signs either from positive to negative or negative to positive. Then you have the inflection point. So just put it in mathematics form and make it easier to apply in the problem. So the second derivative test is saying if you have f double prime is continuous near c, so kind of like you can find the second derivative test, and it's you can find the second derivative near that point. Then you have, if you have c is a critical number and the second derivative bigger than 0, you have a local minimum. If it's a critical number and second derivative negative, so it's local maximum. And just the one thing that you need to really be careful. If it's equal to 0, it's in the second, both of them, first or second. If the first is equal to 0 and the second equal to 0 as well, I'm talking about derivative, then it's inconclusive. So just don't assume anything about this part. However, I would say usually in problems in the midterm 2, to determine if it's a local max or local min, we hardly ever use the second derivative test, because as I say, like it's really clear on the graph. If you can determine if it's on the way to increase and it's suddenly changed to decrease, then it's really easy for you to identify at that point is a local maximum. Usually, in most of the case, we don't use second derivative tests, but for some very complex functions or other purposes, we need to use a second derivative test. But I don't think the exam is going to be that hard. Or some problem you can be asked, given a function f, find a local. Oh, is there a way to taste concavity using the first? And or a way not using the second? Something like that, but it would be used if it was too complex. Well, the thing is, usually the second derivative test you're kind of going to be given is going to be simpler than the first derivative. So say if you're given a function and as you take more derivative, usually it's going to become easier for the second derivative. I don't know how she said something about using the first derivative to evaluate concavity. That's strange. I think what she mean the first derivative is when it come back to this definition. So if you have, so say the graph of f lies above all of its tangent. I actually don't know. I actually haven't really like watched lectures for a while because I've been working with her since last summer. So my slides based a lot on just like the slide that she has, but I didn't listen to her lectures. But can you tell me do you remember like which part is it in the lectures so I watch it and maybe like email you like individually how this thing should be answered? Is it like section 3.3, but like is it just something that she said in the lectures or is it something she wrote down as well? Okay. Yeah, I'll try to have a look at the lecture. So maybe I'll email her like how do we use a first derivative test to check concavity, because to my knowledge I haven't actually be able to do that. I would actually want to learn how to do it, but let's check on that. I'll email her about this as well. But thank you for letting me know. So some problem that we can be asked. No, there's a way, but I Okay. Let me at the end of the sections, out on the way that I downloaded, I'll try to the sessions. I'll try to maybe Google it, how to find it. Okay. So given a function f, problems that you can be asked is you may be asked to find the local maximum or minimum values and interval of increase and decrease, interval of concavity and inflection point. And again, this is just first derivative, second derivative. Sketch your graph based on the information. Oh, this is the one where you actually come to apply what we learned in. That's why I try to make it so visually clear, with going up and going down and all of that. How many inflection points does the graph have given the expression for f double prime of x? And so this is where you have to solve for where you have f double prime of x change the sign from positive to negative or negative to positive. Then you find the inflection point there. Now let's go to the example. Example 3 is question 8 of this section. So you're given this graph, and remember, and please be careful of reading the instruction. So say it's here saying the graph of the first derivative. So this is not the graph of f. So if you're just looking at this and like if it's asking what interval if s is f increasing, and you assume that this is f, the graph of f, so it's completely wrong. So just be very careful, read the instructions, and don't start a problem like thinking, okay, they give us the graph of f is too easy or something like that. So question A, on what interval is f increasing? And so f is increasing, and it's defined when you have f prime of x bigger than 0. So f prime of x is positive. And thank God here you're given the graph of f prime of x. So it's going to be on 0 to 4 and from 6 to 8. Now B, on what value of x does f have a local maximum or local minimum? Now, if you have a local maximum, you have f change from f prime change from positive to negative. So it's going to be so from positive to negative at x equal to 4, and from positive to negative x equal to a. Then this is local max. Now from negative to positive is the local minimum. It's going to be from negative to positive x equal to 6. So this is local minimum. And again, this is because it's based on the graph of f prime. This is not the graph of f. If it's the graph of f, it's way too easy to find it. Now C. This is going to be B. C. On what interval is f concave upward or concave downward? Now, when you talk about concavity, usually the way I use this is use f double prime. But the relationship between f double prime and f prime is that the second derivative is the slope of the tangent of f prime. So kind of like the same relationship between f prime and f. But because here you're given the graph of f prime, so to make use and to find like, the relationship with f prime, this is the relationship. And so when it's concave upward, you have f double prime of x is bigger than 0. So when you're just looking at the graph and find the points, the interval where you have the slope of the graph positive. So this is where you have the slope of the graph positive, and then it go flat, and this goes to 0, and it go negative here, and again it go flat to 0, and it increase to positive again. And so it's gonna be on the interval from this is 0 to 1, because from 0 to 1 you can see the slope of the here it's going to be the slope is positive until this point you have a 0. So you have 0 to 1, 2 to 3, and so again from here from 5 to 6, 5 to 7 is also positive, 5 to 7, and f, so this is concave upward. Now f double prime of x is smaller than 0. Now it's just the rest of the interval from 1 to 2, 3 to 5, and 7 to infinity. This is concave downward. It's because of the slope of the graph. Now, D, what are the x-coordinate of the inflection point? Now, clearly, you can see the fact that f double prime of x changed from positive to negative at x equal to 1. So here, again, from at 2, as x equal to 1 to 2. Why? Because here at 2, you change from negative to positive. And at 3, from positive to negative, then at 5. And finally, it's at 7. Clearly, on the graph, you wouldn't be able to see that this is an inflection point because it doesn't look anywhere. But that's when you think about it. But that's when you think that this is the graph of f. The graph of f prime will lead you to a completely different conclusions. So just be very careful of what you read and what the question is asking for. Now go to example 4. It's question 12. So you're given fx is equal to x over x squared plus 1. Find the interval on which f is increasing and on decreasing. And so you have, again, increasing and decreasing, 5 the first derivative. So you're going to have x squared plus 1 squared. Now using the quotient rule. So it's going to be 1 minus x squared over x squared plus 1 squared. Now, you can, before you go any further, I think it's really important for sometimes you just make the evaluation here. So when you look at the denominator is always going to be positive because x squared plus 1 is always positive and you square it again. So it's going to be even more positive. And so all you need to care about is just the numerator. And it usually is the case of many of the rational functions that we have to use here. Because if you have to consider the denominator as well, it's going to make the questions way too complicated and way too long. And it's kind of like impractical to use it in the exam. So just care about the numerator. And so if you want to find f is increasing, so you just need to, it's just easier way to find this thing is that you solve for this equal to 0. You're going to have x equal 1 or x equal negative 1. And make this table, x and f prime of x. So negative 1 and 1, and then you have negative infinity to positive infinity. Now, clearly in the sense that f prime of x is equal to 0 here. And it's defined everywhere else because the denominator is positive. But in the numerator, it's what we care about. So between negative 1 and 1, if you just put a number in, so they're positive and negative. So based on this, easy, you have decreasing function, increasing, and then decreasing. So it's decreasing on negative 1 to negative infinity to negative 1 and 1 to infinity. And it's increasing on negative 1 to 1. So this is a strange approach, but usually I would highly recommend this because it's make every single interval clearer to you. And if the question asks multiple questions about this problem, this function, then it usually takes much less time to solve end up with, like, finish writing the answer. Then we have B. Find the local maximum and minimum value of f. So again, local maximum, you can use the first or second derivative test, but I would just usually use the first derivative. Is that when you have a local maximum. So local max, here clearly you can see it's at x equal to 1, and local min is at x equal to negative 1. And the value of that is going to be f of 1 is equal to, sorry for this, just keep jumping around. It's half, and f of negative 1 is negative half. Now, last part is C. Find the interval of the concavity and inflection point. Again, I'll use a second derivative. So let me see if when I do it, I don't know if it's gonna be, what question is there? Question 12. Yeah, I only use second derivative. I understand this part when it gets super complicated now and you need to find the second derivative because it's the rational function. So the problem with rational function is that the more you take derivative, it's going to get more and more complicated. So you have it's going to equal this. And so we take derivative here. I'm going to just, yeah, it takes time to do this thing. We have negative 2x. And so next thing is, oh god, this is really too much. Negative 2x, x squared plus. I'm trying to like reduce 1 over x squared plus 1 to the denominator. And so it become easier now. So we finally simplified it. And so what's gonna end up happen is that again we're gonna solve for f double prime of x equal to 0 and figure out which interval will give it positive, which interval will give it negative. And so we can conclude a concavity and inflection point from there. So it's gonna give us x equal to 3, negative square root of 3, or square root of 3. Again, make that interval x f double prime of x. You're gonna have negative infinity, negative square root of 3, 0, square root of 3, and positive infinity. So if you just put a random number in, you're gonna have plus, negative, plus, and this is negative. Just a random number here, it can be negative 1, here is 1, here is maybe like 2, this is negative 2. And so what end up having is that you have concave upward on negative square root of 3 to 0, square root of 3 to infinity, concave downward on negative infinity to negative square root of 3, and 0 to square root of 3. So you have inflection point at x equal to negative square root of 3, 0, and square root of 3. So that's my final answer for this questions. So again, I'm just using the first and the second derivative to come up with these things, and you should be able to do it like pretty comfortably now. Consider the lectures and all of that, and these are just pretty basic stuff coming from the lecture materials. And so I have my final example here, question 45. Suppose the derivative of a function is that one. On what interval is f increasing? And so this is where the table that I used earlier really come into place because it really helps us to solve the problem. So you have f, you were given already the first derivative of f, which is x plus 1 squared, x minus 3 to the 5th, and x minus 6 to the 4th. Now, when you do that, when you set it equals 0, of course you have three values that can give it equal 0, negative 1, 3, or 6. So you have x. I'll make this easier to use and then kind of like come up with the rule that you guys can see here. So this is just extra thing that I think is really helpful. So instead of for the previous table, I only have two rows, x and f prime of x. And the thing that you do is just gonna plug in some numbers and find it. But here, if you look at it, you have a very big power. Like square, and then you have fifth and then fourth. If you plug in a number, it makes the calculations really complicated and annoying. So the way that I'm going to do it is that there's a rule that you can really see from these things is that say you have 0, 0, 0. This one 0 here, 0, and then 0. So everything that you care about in this table is on what interval is these things positive and negative. You don't care about the value. So when you plug in a number, it works sometimes if you have a small number, like a simple expression. But here you have it to the fifth, to the fourth. Thing gets complicated and annoying. So the way that you're going to do it is not plug in number for the entire expression, but you can plug in for the individual one. And there was a rule that I can clearly see here is that if you plug in for square, you know the fact that if you have a square, it's always positive anywhere. And it's just 0 at the point that the thing inside the square is 0. So it's always positive. Similar thing with the fourth power. So it's again always positive. So technically, if you look at this expression, this thing is completely negligible because it's always positive. It doesn't really affect our expression at all. And then again, you have x minus 3 to the fifth. Now this one changed the sign at 3. So it's negative here and positive there. So the thing that you have end up about f prime of x is that it's decreasing from negative infinity to negative 3. And it's increasing from 3 to positive infinity. So the rule that I want you guys to remember here is sometimes you can cut it short in the exam, especially when it's a multiple choice. You have like an expression with a square and the fourth. The first thing you come into mind is that you don't need to care about it because it's always positive. So the only thing that you need to care is usually just the odd power and say any further expression. But if things are factored out like this already, like it's the simplest form. So no need to worry too much about that part. And so that's all I have for today. You have questions over there and some practice problem. And so first is that I'm gonna end the recording, but